Good evening. Today we'll see about a new property regarding the surface tension property. The surface tension is such a binary property. It is not for a individual liquid or individual gas. More or less, we can say that the surface tension will be present whenever the interface of the liquid or gas, or interface of the liquid or solid, or interface of the gas and solid. So it is nothing but a binary property which is commencing or defining an interface. So we'll see about the surface tension property. What is the surface tension? First we will see, and one by one derivation also we'll do regarding this. So first we'll come to the definition and what is the cause of the surface tension. The cause of the surface tension is the fluid. It is actually we are talking about it is a binary property. So there must be two fluids or two substances basically. It may be solid liquid, it may be liquid gas, it may be solid gas. But in that case, the intermolecular attraction forces, that is known as a cohesive force. So cohesive force and another force's name is the adhesive force. That is the intermolecular. That means one liquid molecules, just I'll show you here. So surface tension we are talking about is a binary property. Binary property defining an interface. When this property will comes into the picture, when there is the interface between liquid or gas, liquid or solid, solid or gas, in such a situation, the surface tension will comes into the picture. Now the definition of the surface tension. So definition of the surface tension very roughly, if you are asking, that is the surface energy per unit area, is known as the surface tension or surface tension coefficient. So surface energy per unit area. So energy per unit area, energy. So SI unit, if you're talking about the SI unit of the surface tension, that is energy unit is a joule per meter square. That is the SI unit. But what does it mean by the surface energy? So let you consider here some, that is the fluid static condition. So in a container, there is some amount of the fluid is there, and the above portion there is the fluid, the container, and this is the surface of the fluid here. It is the surface of the fluid, and above the fluid there is some air. So this is the, let you take it is a fluid means water, some liquid, water or some different liquid, and there is some air. So here the interface is there. In this zone, there is an interface between liquid and gas. So at the interface, what kind of the force is acting here? So before to know about this thing, the cause of the surface tension is the unbalanced adhesive force. What is the adhesive force? Adhesive force is between two different and liquids. The force between two different liquids, the attraction force. So here air molecules and water molecules, what is the attraction force? That is the adhesive force. So here how it is unbalanced condition. Now let you consider here for a molecule which is not in at surface. We are talking about some molecules which is not in at surface, just like here, some molecules is there. So this molecules is surrounded by some neighboring molecules. So one molecule is surrounded by some neighborhood molecules. So all neighborhood molecules is attracting the molecule. This is cohesive force. Same molecules, because all are the same liquid molecules. So this is the, so here these molecules is attracted by these molecules. Same way it is attracted by these molecules. In this way, it is attracted by all neighborhood molecules in a spherical manner. So throughout, so it is a statistical average force are the same from all the sides. That's why it is at constant in that position. It is maintaining its own position. So it is this is well balanced here, these molecules. Now if you consider about the molecules which is at surface, the molecule which is at surface or nearby to the surface, this molecule, this side there is a neighborhood molecules is there, this side also neighborhood molecules, this side also, here at the surface also, but in that side there is the air molecules, not liquid molecules. So here the attractive force is present in this show. This all molecules is giving attractive force. But as because of the air is present, so adhesive force is there. So this side cohesive force and this side adhesive force. So due to this cause, some unbalance will be occurred. Due to this force, some unbalance will be occurred in this show. So this kind of the unbalance will be occurs. So only this portion is balanced. But so because of this purpose, it is creating the surface. So surface, in a molecule to be present in the surface, it requires some energy. It requires some energy because here in this condition, all are well balanced. Attractive force all are well balanced. But here there is some unbalance present. So in such a condition, if you want to take one molecules from in this position, from interior any position to the surface, if you want to take a molecules from interior position to the surface, you need to do some work because there is unbalance present and it is well balanced. So you need to do some work, and this work will be converted into there as a surface energy from the energy conservation principle. So a molecules to sustain its own position in the surface, it requires some energy. This energy is known as the surface energy. So if a molecule want to take its position or sustain or retain its position over the surface, then this kind of the energy is known as the surface energy. So surface energy concept, we are getting it. To retain its position of the molecules which is initially at the interface without getting dissolved, it requires some energy. This energy is known as a surface energy. And this surface energy per unit area will gives you the surface tension coefficient, or simply we are telling it surface tension. Either it is called surface tension coefficient or simply surface tension. It is denoted as the sigma. We are denoting this thing as a sigma. There is another definition of the surface tension. This definition is like in this way. So over the surface, if you draw a line, over the surface, if you draw a line, you will see the force will be like in this way. And this force all are in tensile in nature. The force will be act in this way over the surface. If you draw some imaginary line over the surface, you can be able to see some force will be acted, line force will be acted over there. And this line force per unit length can be same way defined as the surface tension. So this line force per unit length. This line force per unit length is nothing but the same surface tension. So the unit of the surface tension we are talking about here, the unit of the surface tension, either joule per meter square or Newton per meter. Newton per meter. Either joule per meter square or Newton per meter. That is the case in here. So that is the definition. So application of the surface tension, where it is. We can see several places. There is the enormous application of the surface tension. That like just a leaf is floating over the surface of the water, or insect is floating over the surface of the water. That is the application of the surface tension. Some bubbles formation is the application of the surface tension. The trees are taking the water from its own root. That is known as the ascent of the sap to the xylem it is taking. There's the capillary action. This capillary action is another example of the surface tension. So there are several examples or applications over the surface tension. So next, we'll see here Young equation, but before it is nothing but a droplet, water droplet. You take it as some water droplet. This is the air. So as it is a water droplet, it will weight the surface. It is a solid surface. Over some solid surface, there is a droplet of water. So this is a water or liquid. So there is a liquid portion, the gaseous portion or vapor portion, the solid surface. Now here one definition I will see here. If you draw a tangential line from here in this zone, if you draw a tangent, this angle is making it, this angle is known as the contact angle. Contact angle. If this angle less than 90 degrees, so we can say this droplet can be able to wet the surface. Droplet can be able to wet the surface. But if this is greater than 90 degrees, so that is not a, the surface is a hydrophobic surface, kind of hydrophobic. That means droplet cannot able to wet the surface. So the contact angle, there is the importance of the contact angle. Now, what type of the surface tension force is acting over it? Because there are solid is there, solid surface, liquid is there, droplet, and air, vapor is also there. So three phase is present. So solid is there, liquid is there, vapor is there. So in between solid and liquid, there would be one surface tension. In between liquid and vapor, there would be another surface tension. And solid and vapor, also there would be another different surface tension. So how it will be looks like, let's see. Here, that is the liquid and this is the vapor. So here, whatever the surface tension is acting, liquid and vapor. In this direction also one surface tension force will be acting. That is a solid and vapor. So sigma solid. And this is a liquid and solid surface. So in this side also one surface tension force will be acting, and that is solid and liquid. Now if you balance this condition, for the equilibrium condition, you are going to balance this thing. Then you take the area is the length is the same. So in such a condition, if you want to balance it, so sigma LV cos theta plus sigma SL will be equal to the so hence you can get the contact angle. That would be sigma ST minus sigma SL divided by sigma LV. This equation is known as the Young's equation. This equation is the Young's equation. It is coming from the equilibrium. This equation is coming from equilibrium. But we don't know whether it is a stable equilibrium or unstable or neutral. This thing we cannot decide from here. Next concept we will see here. Over the curved surface, if any curved surface is present there, if you see any curved surface, this is a curved surface. In this zone is a curved surface. So over the curved surface, one portion is the concave and another portion is a convex. You can be able to see if the concave portion, whatever the pressure, and convex portion, whatever the pressure. So concave portion pressure must be greater than the pressure of the concave portion. In case of in this kind of the surface. We'll see this thing now. So surface tension, so if the surface is a curved surface, it having two sides, one side is a concave, one side is a convex. The pressure in the concave side, the pressure in the concave side should be greater than the pressure of the concave side. So P1 must be greater than that. So the very important equation, Young's equation, we are getting it here. We'll see. Already we have shown it here. So Young's equation, from the Young's equation we can write it down. Contact angle, cos of the contact angle is equal to sigma S by V minus sigma S by L divided by sigma L by V. That is the Young's equation. One more equation we'll see here for the curved surface. Now our consideration is the curved surface. Why it is a curved surface? Because most of the cases, the surface we are getting it like a curved surface. For example, if you're telling it, for example, if you are telling it here, which kind of the surface, just you consider as the bubble or droplets or any jet, water jet. This kind of the surface, you will get the curved surface. So what is the surface tension in there? In case of bubble, you will see there is a liquid layer. In between the liquid, there is another gas. If you consider any bubble, it's a spherical in shape. So outside there is some air, inside also air, and there is a layer of the liquid. There is some layer of the liquid. So this side, so in between a layer. So this liquid and air having one surface tension, plus this liquid and inner air having another surface tension. So surface tension will be double here. And the surface is just a curved surface, spherical inside. That's why we are interested to take the curved surface. What is the equilibrium condition of the curved surface? So let you take here one curved surface. So this is, let you take R1. This curvature, radius of this curvature of this portion is R1 and this portion is R2. We are talking about the radius of the curvature. So this portion radius of the curvature is R1, this portion radius of the curvature is R2. Same way we are writing it here. This is R1, this is R2. And here it makes angle θ1. This is the θ1. And in this side, it makes angle here θ2. It is a two view. It is the front view, it is a side view. It's a looks like it's the front view of this, is the side of the curve. Now here the surface tension is acting over the surface. Here in this way the surface tension is acting. In this way surface tension is acting. Similarly, over this way and this way also surface tension is acting. And due to the surface tension, force is acting over it. So in such a condition, we are interested to finding out what is the, it is actually, this is R1 and this theta. So we can write it down. This is R1, sorry, the angle is very small angle actually. So d theta, we take this very small angle. D θ1, d θ2. Very close angle. So that's right. So here R1 d θ1 and this is R2 d. So we got the curvature, length of the curvature. Some pressure is acting here. So how the curve is looks like, this curve is just, you see from one side we are taking, the curve is like this. So this is the concave portion. This is the convex portion. So concave portion, some pressure is acting, EI. Convex portion, the pressure is atmospheric pressure. And PI must be greater than PA. From the derivation, of course, you can understand this thing, why it is. Whether we are taking it correct or not, then we will see. If PI is greater than PA, so the force will be at this side, above side. The force will be at above side. So force due to pressure difference. The force due to pressure difference will be PI minus PA into area of the surface. So what is the area of the surface? So this curved surface is very small surface, very small differential surface we are taking. We can consider it as a rectangle, elementary. In a rectangle, one side is R1 d θ1, another side is R2 d. because the curved surface is a, though it is a curved surface, but it is very elemental differential area. So we can consider it's just like a rectangle. So the rectangular area R1, R2, d theta 1, d theta is the force due to pressure difference. Now the condition will comes about the surface tension. Now the condition is coming as a surface tension. So here, over this surface, force is acting like this. Similar way in this direction. And what is that force? The force is sigma into this area, this length. Surface tension into the length. Surface tension into R2 d theta. Same opposite side also. Of this portion. So this side also same force, sigma R2 d theta 2. As this length is R2 d theta 2 and surface tension sigma, so the force is acting this way. So it will be looks like in this way, sigma R2 d theta. Force in this side, again same in this side, sigma R2. So this angle is the d theta 1. So half of this angle is d theta 1 by 2. If this angle is d theta 1, if this angle is d theta 1, so this angle will also become this. This angle will also d theta 1 by 2. Same way in this angle also d theta 1 by 2. So this force sine component is coming in downside. Force sine component is coming in downside. Force due to the pressure difference was upward force. Here you have seen the force due to the pressure difference was the upward force. And due to the surface tension, the force is downward force in that case. So force due to surface tension what is that? Sigma R2 d theta 2 is the force sine d theta 1 by 2. Okay, that is downwards acting. Sigma R2 d theta 2 sine d theta 1 by 2. The same for this also. So 2 into. Because one component of this force plus one component of this force that we are considering here. Similarly, what is the force in here? Sigma R1 d theta 1. It's also sigma R1 d theta. Same way, here also sigma R1. The same way in here also the sigma R1 d theta 1 is acting. Here also sigma R1. And this angle, if this angle is d theta 1, so half angle is d theta 1 by 2. So this is the d theta 2 by 2. So same way, this component, sine component also coming in this direction, and this component, sine component also coming in this direction. The same way, we can write it sigma R1 d theta 1 sigma R1 d theta 1 sine d theta 2. Right. Now we are considering here d theta 1 and d theta 2 are very small. So we can write it down. The sine d theta 1 by 2 is nothing but d theta 1 by 2. And sine d theta 2 by 2 is d theta 2 by 2. As the angles are very small. So hence your equation will be reduced to here 2 sigma r2 d theta 2 d theta 1 by 2 2 sigma r1 d theta 1 d theta 2. So here 2 will be cancelled. The same way here 2 will be cancelled. So 2 will be cancelled out here. Now these two forces, if you balance, this force due to the pressure difference and force due to the surface tension are the balance each other. That's why surface is existing. If there is unbalance, the surface will not be stable condition. To get the equilibrium, those two forces will be nullify each other. So force due to the surface tension, we are getting it here. So force due to the surface tension, we are getting it. Now first force due to the pressure difference, we are getting it. PA, inner pressure, internal pressure minus outer pressure into R1, R2, d theta 1, d theta 1. Should be equal to sigma R2 d theta 1 d theta 2 d theta 1 d theta 2 plus sigma R1 d theta 1. So here d theta 1 d theta 2 will be cancelled out from the both sides, and the pressure difference EI minus PA, the pressure difference will be this 1 by R1 plus 1 by R2. So delta P, that is nothing but the delta P, inner and outer side pressure. So here you can see our assumption, whatever it was, we assumed initially we are telling give one statement, and now we are checking the statement whether it is correct or not. PI should be greater than PA because this is a positive term. R is also a positive term, and R2 is also a positive. All are positive terms. So this is must case. So PI always should be greater than PA. So hence we can conclude it, our statement, whatever we are taking it, for a curved surface, the concave side pressure must be greater than the pressure in the concave side. That is one statement we can finding out. Another, this equation, whatever we are getting it out, that is the most important equation, and there are so many questions might have asked regarding this topic. That's we'll discuss. So special case. So whatever we are getting it now, this thing, our equation is coming it at here. Delta P is equal to pressure difference sigma into 1 by R1 plus 1 by R2 is the most important equation. Now some special case, the case 1. We are considering a liquid droplets. We are considering a liquid droplets. So droplet is a spherical inside fully with the liquid. A droplet is a spherical in nature, inside fully with liquid, outside there is some air. Inside liquid, outside air. So as it is a sphere R1, R2 equal to R, radius of the sphere. Because any side, the curvature, radius of the curvature is the same. If you go any side, if you check from any side, the radius of the curvature is the same. Hence, the pressure drops for the liquid will be sigma into 2 by R. So 2 sigma by R. Or we can write it down 4 sigma by D. That is one equation. 4 sigma by D for the case of the liquid droplets. The same way, if you're considering case 2 for the bubbles. How the bubbles and droplets, the difference only it is also spherical. So as it is a spherical, R1, R2 is equal to R, no doubt about it. But here, outside there is air, there is a liquid layer, and again air. So whatever the surface tension, it would be twice. Because one surface tension due to liquid and outside air, one surface tension due to liquid and inside air. So hence here, delta P or twice of the surface tension into 2R. So we are getting 8 pi by D, or you can write it down 4 pi by D. Just double of it. Why it is getting double? Because this liquid layer with the outside air, one surface tension, the liquid layer with the inside air, another surface tension. That is the case 2. And last case we are talking about here, that is the case 3. Case 3 is the liquid jet. One jet of the liquid looks like this. Jet looks like this. It is circular in cross section. One jet from a nozzle. From the nozzle, it is coming one jet. There is a nozzle, some water jet is coming. So this kind of the jet, our equation, whatever the equilibrium equation we are getting it, delta P is equal to sigma 1 by R1 plus 1 by R2. Now, one thing, if you remember, you can get all cases, any kind of the solution. So here, there is a liquid. So a jet surface, if you are taking it, so only one side curvature. So R1 is equal to R, radius of this jet. And R2, if you see from the other side, that is infinite. Because a jet, if you cut the jet, one curvature is just a straight line. So straight line, radius of curvature of a straight line is a jet, looks like in this way. One portion is in this way. What is the radius of curvature? Infinite. And another portion is like this. So that is the radius of curvature R. So hence delta P will be sigma into 1 by R plus 1 by infinity. It is 0. 1 by infinity is 0. So sigma by R or 2 by. So whatever the equation we are getting from the surface tension, we'll list it out here next. And those equation, how much it is effective, we'll see now. So what are the equation we are getting from the Young modulus? We are getting some equation, that is the cos theta is equal to S by V minus S by L divided by L by V. That is the Young's equation. That is the equation number 1 we are getting. Next equation, For a curved surface, the delta P, or inner pressure minus outer pressure, equal to the sigma into 1 by R1, radius of curvature in one portion, radius of curvature is other portion. These two equations are necessary equation for equilibrium. But it is not sufficient. These two equations are not sufficient. It is a necessary equation, but not sufficient. Why it is not sufficient? Because it cannot ensure that surface energy, it cannot ensure surface energy minimum. As the surface energy is not minimum, we cannot say the stable equilibrium. When the surface energy will be minimum, then only stable equilibrium will be established. So stable equilibrium, there is the uncertainty of uncertainty of stable equilibrium. That is the condition in here. But these two equations are very much important equation for the case of the equilibrium case. Next concept we will see the capillary effect concept.